For millions of years, humans have lived as an integral part of natural ecosystems, and we've depended on those ecosystems for our survival. In the last 12,000 years, human behaviour has changed, and we have begun to cause damage to those natural ecosystems, either directly or indirectly. Through our actions, we've derived many short-term benefits, but we are now suffering long-term consequences. If we're going to make better decisions in the future about the actions that we take and stop causing damage to natural ecosystems, we need to understand what they are and how they work. And that's what we're going to begin to do in this episode. A natural ecosystem is a food production and life support system. It works by taking energy from the sun and processing matter from the environment to make food, which sustains all life in every ecosystem on the planet, everything in the biosphere. A natural ecosystem is one part of an organised hierarchy of systems, which ranges from the atom at the bottom to the universe at the top. As we go up through the hierarchy, every system emerges from the interconnection and interaction of the systems below it, which are part of the higher system. Also, as we go up through the hierarchy, every system influences every other system at the same level and every system below that system. The biosphere, atmosphere, hydrosphere and geosphere are the four spheres which combine together on the planet we call the environment. The biosphere is a combination of every ecosystem on the planet, and each ecosystem is made up of populations of different species. Every population is a reproduction system made up of individual organisms, and every individual organism is a system in its own right. Ecosystems are adaptive. They're adaptive in two ways. Individuals have agency, and they can adapt their behaviour to suit their own needs. Species adapt over time through the process of evolution, and these two things combined mean that ecosystems can also change over time and adapt to changes in the environment. An ecosystem is an open system. It takes in energy and matter from the environment, and residual energy and matter goes back to the environment. Energy comes in mainly in the form of light from the sun, and matter comes in the form of the essential elements: carbon, hydrogen, nitrogen, oxygen and sulfur. Those elements come in the form of compounds, for example carbon dioxide and water. The ecosystem uses the energy from the sun to convert the compounds into different compounds, for example sugars, which are the essence of life within the ecosystem. Residual energy and matter leave in the form of heat and different compounds of the same elements. An ecosystem can be made up of hundreds or even thousands of different species, and those species are interconnected and interact with many of the other species within the ecosystem. An ecosystem is an example of a complex system. It is self-organizing, and the properties of the whole system emerge from the interconnection and interaction of the different species. What emerges from every ecosystem is a habitat, and each habitat has its own different characteristics and properties. The Earth has a very wide range of different habitats, from rainforests to deserts, wetlands and swamps, savannas, plains, tundra. There are lakes, rivers, seashores, reefs, and more, many, many more. Each one is very different, with its own distinguishing properties and characteristics. Now that we know what an ecosystem is, where it fits in with everything else, and what emerges from it, we need to try and understand how the system functions, which means how it changes over time. To do that, we need to know how the parts of the system work on their own, and then how each of those parts interacts with each other within the system. To do that, we make a working model. Realistically, we are not able to model everything from the atom to the universe. So we need to set upper and lower boundaries which ensure that all the information that we need is in the model and all the information that we don't need is not in the model, so that it is not overcomplicated. Anything outside the upper boundary is in the environment. We assume that environments are stable and limitless and have no impact on the behaviour of the system being modelled over the time scale of the model. Environments simply provide the inputs and the outputs for the system. We assume that anything below the lower boundary does not need to be modelled. We don't need to know how an individual organism works to know that it reproduces. The only parts that we need to know about are the population systems with their individuals. So we start our model with a single reproduction system. Within every reproduction system, there's a population of individuals. At any point in time, we can count the number of individuals in the population. Because this is a reproduction system, individuals produce new individuals. There are births, and the more births there are, the bigger the population. But there are also deaths, and the bigger the population, the larger the number of deaths. Also, the bigger the population, the more births there are, and the more deaths there are, the smaller the population. What determines the speed at which the population changes are the birth rates and the death rates. This system has a reinforcing loop in the births part and a balancing loop in the deaths part. The reinforcing loop tends to make the population grow, and the balancing loop makes it shrink. What determines whether it grows or shrinks is the difference between the birth rate and the death rate. We now have a reasonable understanding of how a reproduction system works within a single population. But using this model, we have no way of quantifying the size of the population or the speed of change or different rates. In order to do that, we can make use of a computer application which will do all the maths for us. This model is fundamentally the same as the previous one, but we now have quantities and relationships built in which we can vary to simulate the effects of changes in rates. Using the model, we can simulate the behaviour of the system over long time periods, in this case 20,000 years. With the birth rate and death rate identical, unsurprisingly the population stays the same at 1 million throughout the period. But with a very small reduction in death rates from 0.1 to 0.0993, a change of only 0.7%, the population rises to over 1 trillion after 20,000 years. If something happens after 13,000 years to make an equally small reduction in birth rate, The population rises to about 8 billion and then begins to reduce and level out. On its own, a single reproduction system is extremely sensitive to changes in rates and is very unstable. The next thing we need to understand is the effect of populations interacting within an ecosystem. Building on the model that we have for a single population, we can now model two species. One of the species processes matter and grows, and it becomes a producer. The other species eats the producers. It's the consumer. In turn, every species which is a consumer becomes a producer for another species. Our model now has two reproduction systems, one for the producer and one for the consumer. These are the same as the model for a single reproduction system. But these two systems interact within the ecosystem. If the consumer population rises, there are more deaths in the producer system. And if the producer population rises, there's more food available and more births in the consumer system. We've now created an additional balancing loop in the combined system, but what effect will that have on the populations? To understand how the ecosystem functions over time, we need to simulate the new model within the computer application. Once again, this computer model uses two copies of the reproduction system model with the additional links to show how the populations interact. If we run the simulation, we get a very interesting effect. The populations change over time, but they never get very large or very small. Also, if we make small changes to birth rates or death rates, the model does not change. Although the populations are continuously changing over time, the ecosystem remains stable. And as long as it's stable, it's sustainable. This is the key difference between a reproduction system and an ecosystem. As long as the environment remains stable, the natural ecosystem will also remain stable, but the reproduction system will not. It's the functioning of the ecosystem which ensures the stability and sustainability of the emerging habitat. For millions of years, humans have lived as an integral part of natural ecosystems and have shared those ecosystems and habitats with a wide range of other species. Throughout that time, humans have used foraging as their food production system, and we have evolved a range of physical and behavioural traits which have enabled us to survive for all that time. Those traits have not changed, and they are still with us to this day. About 12,000 years ago, some humans began a process of cultural evolution and changed their system of food production from foraging to farming, an agricultural system. It is that change, the impact of that change, that we will look at in the next episode.